In Chapter 5, we start looking at molecules and compounds, and we'll start out by thinking about different ways to view molecules and how to write and view formulas. So starting out looking at a formula, let's just look at a common substance, sugar. So we've looked at sugar molecules and we've looked at these graphite molecules. We've talked about these already previously in other chapters. So when we look at table sugar, we've already mentioned that it is a compound called sucrose. And if we look at a sucrose molecule, we've said that it contains carbon, represented by the black dots, hydrogen, represented by the kind of grayish colored ones, and oxygen, represented by the red. So we can see that the structure of this sucrose is very different from carbon in the form of graphite that we show here, or hydrogen and oxygen put together to make a water molecule, for example. So the water in the tea that you see here. You can see by looking at the molecular representations that these are very different. You would expect them to have different properties. The same thing holds for the properties of elements versus the properties of the compounds that those elements come together to create. So for example, if I look at elemental sodium, we looked at the group 1A compounds, the alkali metals, we talked about how reactive they are. So we know that it's an extremely reactive metal. When we cut it, it's a very dull kind of metal. When you cut it, you do see a bit of shininess, but it almost instantly dulls or corrodes upon exposure to air. So very quick reacting. This doesn't look anything like table salt. Elemental chlorine, if we look at chlorine in its elemental state, it's a yellow gas. You can see it in this container here. If you've ever smelled chlorine from a pool, you know it has a very distinctive pungent odor. In high concentrations, it can be very poisonous, so you know you don't want to be overexposed to chlorine. Highly reactive. It will react with things. That's why we use it for disinfection in the pool, because it very easily and quickly reacts with these compounds and acts as a germicide. It basically kills these things we don't want in there. If we bring these two elements together, sodium and chlorine, in the proper manner, put enough energy into it, we get a reaction that forms sodium chloride, table salt. So table salt, we can see, looks very different from the elemental sodium and the elemental chlorine that we have. So in general, the properties of a compound are going to be different from the properties of the elements that make it up. So you can't necessarily say anything about elemental properties by looking at a compound, and vice versa. Now, some of the substances that you encounter on a daily basis may be elements. They may be just elements in their pure state as you would see them on the periodic table, but most of the compounds that you come into contact with every day are not going to be elements, they're going to be compounds. They're going to be mixtures of those elements. Finding free atoms in nature is a pretty rare thing to have. Okay, so when we look at a compound, we bring two or more elements together and we combine them in fixed, definite proportions in order to make a compound. So a particular compound will always have the same proportion or ratio of elements in that compound. Now, if you have a mixture, you can have whatever proportion you want. So you know, for example, if you have a bowl of Lucky Charms, you can get a bowl of Lucky Charms that has a lot of the little marshmallow bits. It might not have very many marshmallow bits at all. It's still a mixture, and it's still defined as Lucky Charms. But if you're going to have, for instance, a water molecule, which is a compound of hydrogen and oxygen, it will always have two hydrogen atoms for every one oxygen atom, and those will be bound together. You're not going to find three hydrogens with one oxygen and still have a water molecule. You're not going to have four hydrogens to two oxygens bound all together. That is not a water molecule. It's a fixed, definite proportion. So just another example of that. If we look at the figure on the left, this represents a balloon filled with a mixture of hydrogen and oxygen gas. The amount of hydrogen and the amount of oxygen in that balloon is relative. It depends on how much we put in there, but we can still have this balloon filled with a mixture of gas. So it doesn't matter how much of either one I have. But now if I'm going to bring that hydrogen and oxygen together to make that water molecule, again, here's that proportion, 2 hydrogen to every 1 oxygen. It is a fixed proportion. So a balloon filled with hydrogen and oxygen, very different from a balloon filled with water. So this leads us to the law of constant composition. And this was by a scientist, was stated by a scientist named Joseph Proust, who stated this idea formally that elements are going to combine in fixed proportions to form these compounds. All samples of a given compound will have the same proportion of the constituent elements, of the elements that make up that compound. So for example, if we took a sample of water that weighed 18 grams, and we'll see later why the 18 grams in a later chapter, but 18 grams is a good one to start with water. If we broke it down, we would get 16 grams of oxygen and 2 grams of hydrogen. So if we look at the ratio of oxygen to hydrogen, the oxygen to hydrogen mass ratio, we see that the 16 grams of oxygen per every 2 grams of hydrogen gives us a ratio of 8, or 8 to 1. That means there is going to be 8 grams of oxygen for every 1 gram of hydrogen. We're going to put it into a ratio of 1. That's going to be true of any sample of pure water, no matter where it comes from. As long as you don't have other contaminants in that water, which would make it a mixture, it is going to have that ratio of 8 to 1. Now let's take another compound. Let's look at ammonia, which is composed of nitrogen and hydrogen. This is like the household ammonia that you have in bottles under the sink that uses a household cleaner. And if we decomposed it to its elemental forms, to nitrogen and hydrogen, we would discover that 17 grams of ammonia would give us 14 grams of nitrogen, and 3 grams of hydrogen. So again, we can look at the ratio, the nitrogen to hydrogen ratio, okay, by mass gives us a ratio of 4.7, or 4.7 to 1. Now, even though atoms are going to combine in whole number ratios, mass ratios aren't necessarily going to be whole numbers. So obviously, we can't have 4.7 atoms of nitrogen for every 1 atom of hydrogen. But when we're looking at the mass of the compound, that's a little bit different from looking at discrete units. So for example, if we wanted to measure the ratio of 1 basketball to 1 baseball, it would be a 1 to 1. But obviously the ratio of the mass of the basketball to the mass of the baseball won't be the same. It will be different, and it probably won't be a nice even whole number. So looking at this idea that atoms are going to combine in specific proportions to make a particular compound, that allows us to represent that compound in terms of a chemical formula. We can use that fixed ratio of atoms in the molecule. So we've mentioned water. It's a ratio of 2 to 1. So you're very familiar with this formula, probably seen it many times before. So this is going to be the same format we're going to use to write the formula of any compound that we make with elements. We're going to write the symbol for whatever element we start with, and then we're going to use a subscript to indicate the number of those atoms that we have in that compound. So hydrogen, 2 of those. Then we write the symbol for the next element in the compound, in this case oxygen. Now, in this case, we only have one oxygen. We could put a subscript of 1, but it's just implied if we have to write the oxygen anyway, there has to be at least one of them. So there's an implied subscript of 1 on the oxygen. If you ever have 1, it will be an implied subscript. That just means there's one of them. If I were to have any other elements, I can have more than 2 elements in a compound, I would continue writing the symbol and then a subscript for the number for the next elements in the group. If we look at some common chemical formulas, things that you're probably familiar with, table salt is sodium chloride. So we can look at this and now we know this representation means that we have 1 atom of sodium, 1 atom of chlorine combined together in a 1-to-1 ratio. If I look at the chemical formula for carbon dioxide, now I can interpret that. I don't see a subscript here, that's an implied 1, so I have 1 carbon, I have 2 oxygens, so I have a 1-to-2 ratio. If I look at table sugar, the chemical formula for that, C12H22O11. This is one that some of you have already looked at earlier in the semester when you were looking for those common household products when we did our introductions. 12 carbons to 22 hydrogens to 11 oxygen. Now we know exactly how many elements we're dealing with, how to put those together. The subscripts in the chemical formula represent relative number of each type of atom. They are not going to change for a given compound. If I ever change a subscript, I am changing the compound I'm talking about. I'm talking about something completely different. Here's an example of this. If I look at the 2 molecules shown here in the picture, they're both comprised of carbon and oxygen, but they're not comprised of carbon and oxygen in the same proportions. Here I have 1 carbon to 1 oxygen. Here I have 1 carbon to 2 oxygens. All right, so what do we know about these? If we look at this one, CO, this is the chemical formula for carbon monoxide. And you're probably familiar with carbon monoxide. Every year when there's bad cold weather and there are storms and the power goes out, people have generators. And you'll always hear cases in the news of people who either have become sick or even died from carbon monoxide poisoning or being exposed to carbon monoxide. It's an air pollutant. It binds to the hemoglobin in the human body and prevents the body from taking up oxygen, and it can do that very quickly, so adverse health effects for humans. But now if we change the subscript for the oxygen from 1 to 2 by adding that one other oxygen in there, that's a completely different compound. I now have carbon dioxide. It's still not the best thing in the world for humans. It's not something we can breathe, but it's certainly not going to irreversibly bind to our hemoglobin. When we breathe out, we breathe carbon dioxide. We produce carbon dioxide as part of our respiratory process. So we breathe small amounts of it in and out all the time with no harmful effects. So just that slight difference makes a very big difference in the nature of the compound. So you might be wondering, when you write a chemical formula, how do you know where to start? How do you know which element to start with? There's, 117, 18, 19 of these things on the periodic table. Which one do I start with? Well, there is a format for this. When you are writing a chemical formula, it's customary to list the most metallic elements first. So this is where you have to remember that periodic table and remember the location of metals versus nonmetals. So for example, if we look at that formula for table salt that we had, it's written as sodium chloride NaCl, not chloride sodium ClNa, or chlorine sodium. The sodium is the metallic element. The chlorine is the non-metallic, so we put the metal first. If the compound does not include a metal, then you use the most metal-like element first. So the thing that is furthest to the left or furthest down. Remember that metals tend to be found on the left side of the periodic table, nonmetals on the upper right. So the further away you are from the upper right corner of the periodic table, the more metal-like you will be. So for example, we look at compounds written with nitrogen and oxygen. Nitrogen and oxygen, if you look at their position on the periodic table, nitrogen is number 7, oxygen is number 8. So nitrogen is further to the left. It is going to be the more metallic of the two. So we're going to write nitrogen and then oxygen, NO2 or NO, which are two different compounds, not O2N or ON. Okay. So if I'm moving left to right, go with the one that's on the left. If I'm looking up and down a column, elements that are further down the column toward the bottom are going to be more metal-like. So if I look at compounds that are written with sulfur and oxygen, oxygen is number 8 on the periodic table, sulfur is number 16, it's further down, more metallic. So I'm going to write, for example, for sulfur dioxide, SO2, not O2S. All right, so if we look in the book at table 5.1, they give a specific order for listing non-metal elements in a chemical formula. So if there's ever any confusion, for example, if you have nitrogen and sulfur, you don't tend to have just those two together in a compound, but if they're listed together, you know, nitrogen is immediately to the left of oxygen, sulfur is immediately below oxygen. How do you know which one of those is going to be more metal-like? Well, this list shows you that we're going to go with carbon first, then phosphorus, nitrogen, hydrogen, sulfur. So the nitrogen would come before the sulfur in that case, and so on as we go through here. So those are the order that we're going to list nonmetals. If you have carbon, it will come first, followed by phosphorus, nitrogen, hydrogen, sulfur. These are all in compounds that don't contain metals. Now, there are a few exceptions to this, to the rule that you write the most metallic element first. One example of that you're going to see a lot is something called the hydroxide ion, and we're going to be looking at these types of ions in just a minute. And this one is going to be written as OH, and then the minus indicates that it is an ion. It's an anion with a charge. So it's not written with the hydrogen first, which is probably good, so we don't have to go around saying ho, ho, ho all the time. All right, so that polyatomic ion that we talked about, we've looked at these polyatomics. How do we represent compounds? Well, chemical formulas sometimes contain groups of atoms that act as a unit together, not as a neutral compound, but as a charged ion, as in the case of hydroxide. The oxygen and the hydrogen are bound together, but they're not a neutral compound. They have a net 1- charge. There's one extra electron in the whole thing. But we can think of it as a cohesive unit. We can think of it an OH minus the same as we would think of an I minus or a Br minus. So when I have several groups of the same kind present, when I have these polyatomic ions, what I will do is put the formula for that polyatomic ion in parentheses. And we'll talk more about polyatomic ions in a bit as far as what those are. But for now, if you're looking at a chemical formula and you see parenthesis in the formula, that is telling you that everything inside the parenthesis is acting as a unit together. We're not going to break those apart. Those are kind of stuck together. Okay. Now, those groups of atoms, as I said, very often have a charge associated with them. That's what makes them a polyatomic ion. Ion has a charge. Poly just means many, many atoms. So it's got, more than just the one atom in there. Now, to determine the total number of each type of atom that you have in that compound, where you have a group in parenthesis, what you're going to have to do is multiply that subscript. So that like NO2 that we had, that 2, the subscript inside, has to be multiplied by the number outside the parenthesis. So number outside the parenthesis gets multiplied by all the subscripts on the inside to get the total number of atoms. Let's take a look at that as an example. All right, so here's an example of a compound, magnesium nitrate. that contains one of these polyatomic ions, one of these groups. So what it has is one magnesium atom, which would be present as a magnesium 2 plus ion, and we'll learn how to figure that out later. And then two nitrate groups, NO3 minus. We'll be getting to those as a whole list here. So these NO3 groups is one nitrogen with three oxygens bound to it that acts as a cohesive unit. So if I break down this formula, let's look at each part. Well, let's look at the magnesium first. Here's one elemental symbol for magnesium. Now I have no parenthesis, so I don't have to worry about multiplying through by anything. I just look for its subscript. There is no subscript, so that's an implied one. So magnesium, I have one of those, one magnesium. All right, now let's look at what's in here. This is actually two different elements, nitrogen and oxygen. So I'm going to start with the nitrogen. If I look here, just within the parenthesis, what is the subscript for the nitrogen? Well, there isn't one. Again, that's an implied one. So that indicates I have one nitrogen for each one of the NO3 groups. So I'm going to write a 1 here. Now, this is in parenthesis, so I have to multiply by something. And I multiply by the number that's out here, this 2. 1 times 2, I have 2 nitrogens. Now I do the same thing for oxygen. I look at this one, here's the symbol for oxygen, so I've got that. It has a subscript of 3, that means there are 3 oxygens for every NO3 unit. And then I have a 2 out here, which tells me that I have to multiply through by 2. I have a total of 6 oxygen atoms in that formula. So that's how I'm going to break it down to determine how many atoms I'm dealing with. So when we talk about chemical formulas, we can subdivide. We categorize all the time in chemistry, and we're going to categorize types of chemical formulas. There are several basic types. Okay, one is an empirical formula. The empirical formula just gives you the relative number of atoms of each element in the compound. So this is like least common denominator. What is the minimum ratio of atoms to one another within the compound? Now, you can have also a molecular formula. A molecular formula is going to give you the actual number of atoms of each element in a molecule of that compound. So one example of this, if you're familiar with hydrogen peroxide, the topical cleaner that you have at home comes in a brown plastic bottle usually, usually a 3% solution. If you look on the label, they may give you the formula, the molecular formula. The molecular formula for hydrogen peroxide is H2O2. I have 2 hydrogen atoms and 2 oxygen atoms bound together. I have to have 4 atoms to have a molecule of hydrogen peroxide. But if I'm going to break it down to its simplest ratio, how many hydrogens per oxygen? I have 2 to 2 or 1 to 1. So the empirical formula of hydrogen peroxide is HO. Now don't confuse this with the formula for the hydroxide ion that we talked about. We said that one was written as OH minus. OH minus is different from this empirical formula. And you probably won't ever see this empirical formula again anyway, because again, we can look at an empirical formula, the relative number, but the information we want is really within the molecular formula. This is what we need to know. What's the real ratio? If I were to somehow be able to hold a molecule in my hand, how many hydrogens, how many oxygens would I have, and how are they put together? Now, a molecular formula is always going to be a whole number multiple of the empirical formula. So obviously I can multiply through by a number to get the molecular formula. I multiply through by 2 to get to the molecular formula here. For many compounds, such as water, sucrose that we looked at, C12H11O22, or C12H22O11, sorry, it's been a long day. If you look at that, there is no way to simplify that formula. So very often the molecular formula and the empirical formula will be the same thing. But if you can simplify it down, then you would have two different. You would have an empirical and a molecular formula. You can also have what is known as a structural formula, in which we just use lines to represent chemical bonds and show how the atoms in the molecule are connected to one another. So there's a lot of information we can get out of a molecular formula, but it's just letters and numbers written down. It doesn't show me how these are put together. This would be like trying to put together Legos, and they said, okay, take 12 red and 8 blue and put them together. Well, it didn't tell you how. You don't have a roadmap. Structural formula is a great way to get that roadmap. That's the picture that you get with your Legos. How do I put these things together? Sorry, I tend to use Legos a lot because I have two preteen boys who are really into Legos, and also Legos tend to relate to molecules pretty well. So we can think of little atoms and molecules as Legos. All right, so here's kind of a summary of different types of chemical formulas that you might see as visual representations when you're looking at these. You can have a molecular model, which is just a three-dimensional representation of the molecule you're looking at. Molecular models come in several different flavors, if you will. One of the most common ones is the ball and stick model, and you'll see that a lot. There's another one called a space-filling model that you'll see. If you have a ball and stick model, you can think of it as though the atoms were balls. You can think of them like little round gumdrops, if you will. The chemical bonds are sticks. If you took lollipop sticks and stuck gumdrops together, that would be kind of a ball and stick model. The idea is that you put together a ball and stick model to represent the shape of the molecule, because these things are not flat on a piece of paper. They do take up space in 3 dimensions. So that's what we want to represent. And usually when you see a ball and stick model or a space filling model, as we'll see here in a minute, the balls are going to be color coded to represent elements. Each element is assigned a color. Now here are the most common ones that we'll see. It obviously is not every element that's out there, but these are the ones that we see over and over again. So standard notation will show carbon as being black or dark gray. Hydrogen is usually a white color. Nitrogen is a pale blue. Oxygen is red. Fluorine is a pale yellow. It kind of represents the color of fluorine gas. Phosphorus is a deep blue. Sulfur is yellow. And chlorine is green. And you'll notice kind of relative sizes here. That kind of represents the relative size of the atoms. Now in a space-filling model, what they're trying to do is more closely represent how we think a molecule might appear if we could blow it up to a visible size, if it weren't submicroscopic. If we were to be able to take a molecule and expand it to a size we could hold in our hand, we wouldn't be able to see the sticks or the bonds holding the atoms together, because the balls themselves, the bond is basically keeping the nuclei pulled together, and there's overlap of where the electrons are. So the overlap of the electrons within these two atoms is going to obscure, where you might have a quote stick. There's not a space between these things when they're bonded together. All right, so let's look at an example of a molecule with these different representations. We've chosen methane here as a molecule for a comparison of these formulas. So when we said we start with a molecular formula, now keep in mind, if we look at this, molecular formula is the same as the empirical formula here. We don't need to show an empirical formula. This is how we would represent the molecular formula of methane. 1 carbon, 4 hydrogens, CH4. Now the structural formula, what I want to do is show kind of how the atoms are connected. So each hydrogen atom is bonded to the carbon. It's just showing you where the bonds are. Now notice, this is not really much of a three-dimensional model. We've just drawn it flat on a piece of paper. So if I could look at a methane molecule, is this what it would look like? Would it lay flat on the paper and just come out in an XY axis from the carbon? Nope, not going to do that, because these atoms have these electrons, and the electrons, as much as they want to get near the protons in the center, we know that for magnets, if we try to put like charges together, they repel each other. Same thing with these. If they've got all these electrons floating around out there, they don't want to be next to each other. They just want to be next to the thing in the middle. So they're going to push each other out of the way into a three-dimensional shape. And that's what these two, the ball and stick model. So here you see the bonds in between, like sticks. Here's a space-filling model. This is more of a real representation. You see that there's an overlap in the spheres. You can't see the sticks that are holding it together. These allow us to see what's known as the geometry of the molecule. If I could look at this thing in 3 dimensions, what would it look like? And we will talk more about molecular geometries in later chapters. So we're going to use images to try to make a connection between what we see around us and what is going on the microscopic level in the world of atoms and molecules. So the macroscopic world is what we can see with our eyes without using microscopes, or in the case of atoms and molecules, we have to go even further to be able to see anything. The atomic and molecular world is going to be composed of these particles that we're talking about. So we have to be careful in the way we symbolize the atomic and molecular world. We can do that. So here's a representation, and we will do this very often. But what we need to keep in mind is that this really is a representation or a model. And when we're talking about things on an atomic level, they don't always play by the same rules that we're used to on the macroscopic level. So just be careful about making implications, about making implied assumptions about what you're seeing in the models. Remember, these are just models, and models have limitations. So for example, if you look at a road map, you know that that's a model of a place, of somewhere that you may be traveling, but we would not presume that a two-dimensional map is going to be the same as the three-dimensional place we're looking at. We wouldn't think that it was perfectly flat. We know there's changes in elevation. It's going to look very different. Same thing here. These are models. They're maps. They're things that we're using to help with our understanding. All right, so we talked about the classification of matter, and we talked about the fact that we can have pure substances or that we can have mixtures, and the pure substances got broken down into elements or compounds. So now we're going to take it a step further. Elements may be either atomic or molecular, so we can subdivide classes of elements, and we'll look at what that means. Compounds are going to be either molecular or ionic. So we're going down another step in that chain. So here are the elements and compounds where we had stopped. Elements are either going to be atomic, such as neon, where in the elemental form they exist as individual free atoms, or molecular, where the free atoms do not exist on their own. They come together and bind with one another to make a compound. So this is an element, but it's an element in a compound form. This is molecular. Now compounds, and I say a compound, it's not a compound in the sense that the other compounds, a compound will have two different elements in it. This has the same element, but there's two atoms of it, so it's a little bit different that way. Now a compound can be molecular. So as we have here, H2O, things are bonded together, but then each molecule can act in freedom, or we have what is known as an ionic compound, where things are held together by charge, by a very strong difference in charge. And when we have this, we don't really say that we have a molecule, we say that we have a formula unit. Now you'll hear people say sodium chloride molecules, they'll use them interchangeably, but be aware to be strictly kosher about it, if you will, to be absolutely following the rules on it, you have to say that an ionic compound has a formula unit. And notice that it is not shown as just one of these little units floating free. They're stacked in this regular structure. So this is going to be different from the molecules that we see. So let's talk a little bit about the elements here. Elements, as we said, are either atomic, which are those that exist in nature with single atoms, and most elements are going to fall into that category. So you're not going to have to worry about most of the elements. But there are a few, there are about 7, that do not normally exist in nature in single atoms. They exist as what we call diatomic, or there's actually a couple of polyatomic molecules, where you get 2 or more atoms of that same element bonded together as the base unit. So that's your molecular element. Here's an example of an atomic element. If we have mercury, now notice that these things are stacked in here. They look a little bit like the formula unit that you would have in an ionic compound, but they're not being held together by any sort of bond in there. I mean, they're just basically stacked together. I could easily take mercury and heat it up and have these free themselves and evaporate off. It wouldn't take a lot of temperature to evaporate mercury. Now we don't want to do that because mercury is very toxic to us, and putting it in a gas would make it very easy to inhale and ingest. But you could do that. So those are freely moving around over each other. Each one is individual. If we look at chlorine, okay, these are diatomic. So I need to have 2 chlorines come together. They're bonded together. Now each one of these can act as a separate unit and will move around freely, but it stays bonded to that other chlorine. All right, so we said there are about 7. What are those? You're going to need to know these. You're going to need to remember the elements that exist as diatomic molecules, because when you use these in reactions, when you start with them in their elemental form, you will have to represent them as their diatomic molecules. All right, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Here they're shown on the periodic table, and you can see they're clustered in a particular location. So the ones that are in purple are the diatomics. So I would always have H2, N2, O2, F2, so on and so forth. Now these 3 that are in green, these are polyatomics. Now your book doesn't mention this, but I do want to mention it because you won't see them represented as just phosphorus, sulfur, or selenium. They don't exist in that form. They exist in polyatomics. Phosphorus has a couple of different forms, but the more common one and the more stable one is P4. And so 4 atoms are held together in this particular arrangement, and that's how you'll find it elementally. Sulfur, if you have ever seen a piece of sulfur, bright yellow, kind of smelly stuff, if you've ever had an old-fashioned match, or when you light a match, there's still sulfur in matches. That's that distinctive smell you get when you light a match. If you have old-fashioned matches that are pure sulfur on the head, you would see that the sulfur is in this form. There are 8 atoms of sulfur bonded together in a ring. It's a little hard to see here, but they're actually in a ring together. And that is the sulfur polyatomic molecule. Selenium, very similar. All right, now, so that was elements. Now let's look at compounds. They can be either molecular or ionic. Molecular compounds are going to be compounds formed from 2 or more non-metals. So we know that the number of non-metals is much smaller than the number of metals. So as you can imagine, you would think that there probably aren't that many molecular compounds, but the way in which these non-metals can bond together, there are an infinite variety of ways they can come together. So there are actually many, many compounds that are molecular. So we're going to have to learn to look at a compound and be able to determine, is it composed of metal and nonmetal, or is it just nonmetal? If it's just nonmetals, it's molecular. If you have a metal anywhere in there, 1 or more metal or cations, So there are a couple of polyatomic cations, but generally speaking, every cation is going to have a metal in it somewhere, with one exception. When we pair a cation with an anion, that's when we're going to get an ionic compound. All right, so if we look at a couple of examples here, the one on top is carbon dioxide in the form of dry ice. So if I take carbon dioxide gas, I put it under high pressure and I lower the temperature, I can get it to convert to a solid form. And if you've ever gotten some dry ice or played with it, you know it's a lot of fun to play with. It's got a lot of interesting properties. Right? So the molecules that are in there are these carbon dioxide molecules. This is molecular. Carbon and oxygen are both nonmetals. Now if I go back to my table salt and I look at this one, the basic unit here is going to be sodium, which is a metal, and chlorine, which is a nonmetal. So this one does not form a molecule, it forms a formula unit. This is an ionic compound. All right, so metal and nonmetal, that's going to be an ionic compound. Nonmetals only is going to be a molecular compound. All right, so a little bit more about ionic compounds. Okay, when a metal, which has a tendency to lose electrons, remember we said that metals they want to move toward that noble gas configuration, and it's easier for them to back up usually on the periodic table to go back, so it's easier for them to lose electrons. They form positive ions, cations. They tend to combine with nonmetals, which for them it's easier to go forward, gain some electrons, and form an anion. Okay, so now I've got a positive charge and a negative charge. Opposite charges attract one another, and so we get those positives and negatives binding together. They're attracted and they form that formula unit. All right, so metal, nonmetal, you've got it ionic. Base unit is a formula unit, not a molecule. All right, so ionic compounds don't have individual molecules. You can't go in there and pull out, you know, a sodium and chlorine molecule. It won't hold together that way. What you're getting is a three-dimensional array. Now you can look at what's the base unit repeating within that array. That's the formula unit, but they're going to want to stick together. You're not going to ever find a tiny little grain of salt that has one sodium and one chlorine in it. They're going to bond together.